to have Don Sloan as our guest today, who's going to help me out with this topic, QAM, getting data on a wave. Before we share slides, just a little bit of background on Don. Don, when Cisco, or I'm sorry, when Seven Signal came over from Finland back in 2012, Don was brought on board to help us out. Don was at Cisco. Before that, he was at Aeronet. Um, Don, how long were you at Aeronet exactly?
I guess, depending on how you count it, Aeronet was acquired by Cisco, so I remember having a 15-year anniversary, but I guess I was at Cisco 8 years after being acquired in 2000.
And then before Aeronet, where were you? Was it Telzon?
Yeah, there was a small company here that I joined because they were buying Motorola products, and in fact, I worked at Motorola for 12 years before that in the radio design labs.
And then at Motorola, so this is going back definitely to the origins or the beginnings of Wi-Fi. And before we got on today, you were telling me a little bit of a story of kind of the origins of Wi-Fi and what the first big use case was, and the real, the reason why we needed some kind of technology. And this was while you were at Motorola, and kind of give us a time frame. Was this back in the mid 80s, late 80s?
Late 80s, actually 1990.
Okay.
It was well, go ahead if you're going to talk
No,
some.
no, go ahead. I want you to tell the story about, something came along in the Chicago area, and all of a sudden there was this need for this new technology. Why don't you tell the story, Don?
Yes, the Chicago Board Options Exchange. They used to do all the hand signals, ordering out on the floor. And the story we heard was that at the end of the day, those were only 80% accurate. And the Federal Trade Commission said you can't do that. You've got to have some technology. You got to have something to make this better. So the CBOE actually put out a request for proposals for a broadband wireless system that would solve their problem. And the new thing on the block at that time was spread spectrum, was the only radio system available, for commercial use that offered anything greater than, just, 1200 baud or something like that.
Mhm.
And so many companies jumped on board to come up with a proposal, and we did as well. Uh, Actually, that went on for 5 years. Nothing really came of it for a while, but we ended up with a customer, Walmart, who liked our product, and we rolled it out at 3,000 stores. And so here we were in the spread spectrum business. And that was a 900 megahertz product. Spread spectrum is 900, 2.4, and 5 gigahertz at the time. And then IBM saw what we had and wanted to go international. So we had to have 2.4. So,
Mhm.
of course, we started designing a 2.4 gigahertz radio. And about that same time, 1991, the Ethernet Alliance had about finished up 802.3 Ethernet standard, and they
Mhm.
spun out a group to start out 802.11. And so that's where IEEE 802.11 originated. And so, of course, we were charter members and
Mhm.
contributed the first QPSK PHY modem, to that standard. And so that's how it began.
I remember you also telling me the story of, some of the early use cases, the car rental, they wanted to be able to scan, I think you scan the receipts. Tell that story really quickly.
Yes, Avis Rent-A-Car was
Davis,
number
yeah.
two to Hertz, right? And so they try harder, I think was their motto. And so we sold them our first handheld with FM radio back in 1986 at Telzon. So they could go out to the parking lot and check your car out or in, I guess, on the spot. So that's how we first started with mobile data with wireless.
Well, with that said, I think it's a great segue into our topic today, which is getting data on a wave. My goodness gracious. I mean, how far we've come since those days, Don. So what I'm going to do here is share this presentation, and we're going to kind of walk through this evolution here because it really is remarkable. Just give me the thumbs up, Heather, if you could see that okay. All right. So, I mean, you've been doing this for many, many years, Don. I'm relatively new. I've only been doing this for 10 years. And I always like to joke, I kind of play an engineer here at Seven Signal, but you are a real wireless engineer, a real engineer, electrical engineer, I believe, correct?
Oh, yes.
Yeah. So, so I'm really glad to have your support today. But we're going to try to break this topic down because, there's a bit to it, but it is really important. If you're a Wi-Fi person, if you like this technology, then this is for you, because this kind of detail is really important to just understanding, how Wi-Fi works, how it doesn't work. So we're gonna try to walk through that today. And when Don and I were putting together this presentation, we decided that the smartest thing to do is, hey, let's just start with AM FM. AM FM is something that a lot of us can wrap our head around. This is where we're basically taking a carrier, away, a signal, and we're modulating it. And we can modulate it, the height, okay, and that's amplitude, or we can modulate the frequency. And that's FM, frequency modulation. And so by doing this, what are we doing? We're creating ones and zeros. All right, we're creating ones and zeros, and ones and zeros. This binary code is what we use in order to transcode or create messages. And again, that's kind of the simplest thing, and kind of the base layer of this whole thing is modulating amplitude and modulating frequency in order to create these ones and zeros. Then something else, and the next part of this comes along, and that's with this right here. And that's BPSK, binary phase shift keying. And Don, if you can kind of explain phase shifting to our audience here, that would be great.
Yes, you showed AM and FM. Obviously you have to have a radio wave because that's what propagates through space. Don't even have to have air. You were actually showing an analog sine wave information being carried on the peaks of the AM. But we like to use phase shift of the carrier to convey digital modulation. Modulation just means we're somehow affecting that carrier or modulating it to carry the information so that it can be demodulated at the end point at the receiver. And by shifting the phase of the carrier, you can see at the bottom line there, the sine wave of the carrier was coming up, and that was the edge of a bit, and so it reverses and goes right back down. It's a 180-degree phase shift, or actually a flipping of the sine wave.
So if it was like this, then it flips, and now it's like this.
That's right. And so we detect that at the receiver, it flipping back and forth, and we can extract then the original binary code that was sent from the transmitter.
Excellent, excellent. And this is, the amplitude modulation, phase shifting. These are the primary components of QAM, Quadrature Amplitude Modulation. Because what QAM does is we're modulating both phase and amplitude of that carrier wave. And so this out of phase, this shift that we're talking about here, Don, we call it's orthogonality, and another word for that is quadrature, right?
When it's 90-degree phase shift between two sine waves, they are said to be in quadrature. And there's some unique properties about that. I like to think of an analogy of orthogonality is the other word you had there. An analogy of orthogonality is you can think about a moving object. Say you're either driving a car or you're running, you're headed north, and the wind hits you directly from the west at 90 degrees. It doesn't change your forward speed at all. It doesn't slow you down, it doesn't speed you up, but it just moves you sideways. And so those two orthogonal forces do not alter each other, but they contribute to a single resultant. And that's what we're going to do with quadrature amplitude modulation. By having two inputs in quadrature, non-interfering, we can convey a two-dimensional picture essentially, and we'll get to that.
All right, awesome. And why do we do this? We do this because of the need for speed, right? So what we do this this technique to transmit more bits per, and then we introduce something called the symbol, which is basically multiple bits. And we do this so that we can send more data in less time because of the need for speed. Don, you told me a funny story about how a long time ago, when things were just getting going, how there was a time when people didn't think that there would be a need for any more speed. What was that again?
Well, actually, when we were on the standards committees, and 802.11 came out, I believe, 1997, and then A and B came out in 1999. Well, A was working on 54 megabit, 6 megabit to 54 megabit.
Yep.
And the rumor was, we don't really know if 54 megabit can work in a noisy environment at all, but it'll certainly work at 48 or 24 megabit. So look where we've come. Now we're talking hundreds of megabits and even gigabit. So
Oh my gosh. I know it's really amazing how the technology has changed. All right, let's move on. So now let's talk about this quadrature carrier concept, this idea of combining, doing two things at once. Take it away, Don.
yes, there's a unique property of a carrier wave, which we can create by starting with two carrier waves, 90 degrees out of phase, again, this orthogonality, and we can modulate those two carriers independently. So, you have the green there is 90 degrees out of phase with the white. Those are two carrier signals, and I can modulate those independently. The
Mm,
cute thing is we can then add those two, and we'll show that in the diagram next.
yeah.
We can add those two modulated waves that are orthogonal to create a single additional waveform. Anytime you add two sine waves, you get a sine wave. Well, it happens to be that sine wave will be halfway between the original two in phase if the amplitudes are the same. And so that red carrier we're showing down there will be carrying the quadrature information. It will be carrying two bit streams independently modulated, which we can then combine in a two-dimensional fashion to give us that square constellation you see.
That's right. That's right. So the two into one. And another way to kind of look at that is like this. Why don't you explain this?
Yes, the top diagram there is the transmitter side. So you can see I and Q. We talk about I as the in-phase signal and Q as the quadrature signal. We'll feed that into those X's or mixers with a single RF generator between them. And the top mixer is going to get a zero phase carrier, and the bottom mixer is going to get 90-degree phase shifted, as I showed in the previous diagram.
Yep.
So we have the exact same frequency and two separate information streams coming into these. So we'll have two separate modulated carriers. Then we add them. And being there at the exact same frequency with different modulation, we get a single carrier out, which is carrying both modulations. And then the bottom diagram is the receive side, just reverse the process. We receive it there on the left, moving to the right. We split it back apart. That should be shown as a splitter instead of a summer. Split it back apart, actually just sending the same signal to both mixers with a local oscillator, again with 0-degree phase and 90-degree phase relative to each other. Everything's relative. And also relative to, you have to actually lock on to the incoming signal sync pattern. And that will then reproduce, separate out the I signal. You see that I of t, whatever that waveform was,
Right.
and at the bottom the Q of t signal. So we will take a 8-bit number, put 4 bits into the top side and 4 bits into the bottom side and send it over. And at the receive end, pull it back apart and reassemble the 8-bit number, which we can show.
Yeah, and there you have it. So the combination or this phase shifting concept is absolutely critical here. All right, and that leaves us to QPSK, which a lot of people have heard of, quadrature phase shifting or phase shift keying. We're still talking, I mean, and again, ones and zeros. This is binary, it's one bit, but why don't you explain? This kind of takes it to the next level in terms of the two merging into one.
Yes, the original was a simple binary on the horizontal axis and binary on the vertical axis. And that is just called quadrature phase shift keying because it only comes up with the 4 points you show
Right
at
here.
the bottom left corner. And so we're mapping what is in any one instance, instead of what bit are we on, what phase and amplitude are we on. So if the I signal, the in phase signal is a 1 and the quadrature signal is a 1, then we'll have that top right quadrant, the next one over, 1, 1
Yeah, 1, 1, right.
and so forth. It's pretty obvious. So those dots will kind of be lighting up one at a time, like a Christmas tree, I guess, as these ones and zeros go by. But you can see it and visualize it as a two-dimensional pattern.
And now we add in amplitude. And we were talking about this the other day and how amplitude allows us to, like, think of it, this stair step pattern allows us to basically, add more bits. Go ahead.
Right, exactly. This is here showing 16 QAM, where it's 4 by 4. You have 4 levels presented to the in phase side and 4 levels presented to the quadrature phase side. And those are both coming over the same carrier. We pull it back apart at the receiver. And you can see that 2 bits will give us those 4 levels. So I have 4 bits of information I'm sending, and each one of those dots is a symbol, which I think you have some more cute pictures of.
I do. So let's take a look at that right here.
Right, so each of those symbols on the right are the 16 possible combinations of, a 4 by 4 constellation. And there you see the different amplitudes and different phases. The dots closer to the origin in the middle have the lower amplitude. The dots to the outer, the periphery, has the full scale amplitudes in those scales. And if you look closely at those 16 different waveforms, they start at different phases.
Yep.
Some of them start at 0, some of them start at 1. So that is the phase amplitude characteristic of QAM.
Yeah, these are, I mean, these are the waveforms. I really like this picture, Don, because it actually shows the waveform and you can see how they kind of start at different spots along the way in order to create the symbol. The symbol that is, 0, 0, 0, 0, 0, 0, 1, 1. These are the 16 different symbols, and this is
Right.
carried
That's
data.
that's the analog waveform that we're actually decoding back at the receive side to get us this constellation that you're showing on the left.
Yeah, and a constellation, I mean, it's a good term because it is a map. We're mapping, as you can see the little animated GIF go here, the amplitude, the phase in terms of, degrees, and then what that equals in terms of a symbol and where that symbol resides in the constellation, right?
Yes, and note we're getting 4 bits. In the same time period, we would have gotten 1 bit of information
That's right.
with,
From QPSK to now 16 QAM.
well, QPSK is in between, but from binary shift keying to here, we have 4 bits instead of 1 bit.
Amazing. Amazing. Wow. All right. So then, I mean, when you look at this, it's like almost incredible. But then when we kind of make jumps like this, it gets even more incredible. How impressed were you, Don, when we went from 16 to 64, from 64 to 256? I remember a few years ago, you were like, wow, is this really going to work? And it's just incredible, isn't it?
Oh, it is, but the technology keeps getting better. Our radios are getting higher fidelity, if I can call it that, better, more accurate, and less noise when you have a good signal, less internal noise. The silicon is getting faster and better, so the capabilities are there. But you see here, the 256 QAM will give you an 8 by 8 um, uh, an 8-bit data, and the issue becomes one of how well can you maintain that over the air. In other words, noise has a very significant effect on that. What
Mhm.
happens when a signal, one of those, your carrier signal and its modulation are affected by a noise source, those dots tend to blur out. They get bigger and they start to overlap each other. And as soon as that blurring of a phase state crosses over a boundary into what could be interpreted as the other phase state next to it, then you get a bit error. And now you're relying on, our error detection, error correction to try to correct for that. And then we'll normally shift down. And as 802.11 has progressed, you see we've moved up to 1024 QAM, which of course is like a 16-bit number. And wow, that's great. You can get, each time we do that, we get twice the number of bits, which of course increases exponentially the amount of information we're sending. But the requirement for signal to noise ratio becomes incredibly high. So this is going to work for you in the same room, maybe next room over, but you're not going to get a great distance because noise comes up with distance on a radio system, and we're just going to get too many errors with the highest rates.
And there's an error, there's a tolerance, and then after a certain number of errors, then we're going to step down to a lower modulation. Like we're going to go, from, and this is where MCS comes in. We're going to go from an MCS, 10 to down to 9, down to 8, right?
Exactly. We'll retry at the higher rates, and
Mhm.
there's all different algorithms from the different vendors as to how many times do we retry. I mean, there
Retry.
is, guidelines and standards, of course, but some differences creep in. But anyway, we'll retry several times at the higher rate, and if that doesn't work, we'll go down to the next rate, and if that doesn't work, we'll go down. And of course, most of all of the executive uh, uh, information is sent at the low rates, the base rate, just to get started, to get associated and authenticated, and then we'll move up and try to run the high rates to get the throughput.
Right. But I think the point that you wanted to make on this slide is just how pristine the environment needs to be in order to go fast. I mean, we're talking about, trying like yesterday we were talking about an archer, and it's like you want to hit that bullseye, and that bullseye, is really, really small, getting smaller and smaller, and then you take wind into account and everything else. In order to go fast and really hit the dots on the screen, so to say, it needs to be a nice environment.
Exactly. That's right. The dots become increasingly small bullseyes. That's a good analogy, I guess.
So we have come pretty far, and this is really, where we are today. Some pretty significant jumps in the past 10 years or so, going from 64 to 256, from 256 now we're at 1024, and I mean Wi-Fi 7 is here already. 4K QAM. I mean, in your wildest imaginations, Don. I mean, could you have even thought of that a few years ago? It's just amazing.
Exactly. It is.
So just the number of dots and the number of symbols, but that's how we're transmitting so much data so quickly now is through this technology, through this quadrature amplitude modulation, just like Don said, where we're taking, the phase shift, and we're taking, what's on the Q axis, which is the quadrature, and then the I axis, which is the correct, help me, the
The, the in phase
in phase. Okay,
or
and then
incident wave, yes. Mhm.
in order and combining them. And just to go back a little bit, because I really liked this right here, where it shows on the one direction and then in the other direction, how I'm creating through the stair step fashion, with modulating amplitude, and creating these symbols. And then that leads us to this. I mean, really getting an understanding of 16 QAM is kind of, the most important thing. I really like this picture because it does help with identifying, oh, wow, we're creating these little symbols. I get it, by amplitude, with phase shifting and with amplitude, in order to create these little different waves, and these different waves then map to bits,
Right.
right? And it's pretty cool. That's pretty cool. So, guys, that's what we wanted to talk about today. I mean, it's a pretty complicated subject, of course, but I mean, we tried to break it down for you in a way that hopefully was pretty easily digestible in a small amount of time. I have a feeling that there are a ton of questions out there. And Heather, what we're going to do is we're going to turn over to you to kind of see if there are some questions out there that maybe we can answer on behalf of our audience. Why don't you take it from here?
All right, let's do it. We'll give them a couple seconds. I'm gonna comb back through the chat really quick, 'cause I think I saw one question. No one seems, so I'm reading this out loud, so excuse me if I mispronounce anything. One question no one seems to know, I can never get an answer, is with QAM, how many dB differences in amplitude is needed, or I guess how much dB difference in amplitude is needed for the steps of the AM portion of the modulation in the constellation of 1024 QAM? Does Wi-Fi need to see the states?
Okay, so it means steps. So if it's 4 in this picture here, then it's going to be 8 in order to get to the next phase of modulation, right, Don?
Well, I think he's asking, that person was asking, how many dB
Oh,
stronger signal do I need? Is that what it is? How much
yeah,
stronger does a signal need to be?
I think
And,
so.
we're on the order of like 30 dB signal to noise ratio is required. I mean, it's a gray, I mean, a fuzzy area. It depends on the type of noise and the situation of reflections and all of that. But you do need about 30 dB stronger
Got it.
signal noise ratio.
Cool. All right. Wow. This is maybe a record. You did such a good job. Oh, okay, good. We got one. I was like, you guys did, you explained so well that no one has
Mm,
any questions. Like
That's
this.
not true. Go ahead.
Okay, Andrew, how reasonable is it to get QAM 4K in real world environments? It seems environments are getting noisier over time, not quieter.
Well, as we said, it depends on the environment, of course. This, I think, is what you're going to use in fairly close proximity. They talk about, within the same room where there isn't too much reflection, multipath distortion, uh, highly variable. And to be honest, I don't have experience with 4K QAM out in the field yet.
You
Wi-Fi
do.
7 is still in development and is coming out with various vendors, I know, but I can't give you a real concrete number on that.
But one of the things that you mentioned, Don, was that the radio sensitivity and the filtering and all of that is actually improving as well, right? That's going to assist.
Yes, but the environment becomes the dominant factor.
Okay.
I mean, this stuff works great on a cable, and in fact, a lot of cable modems, are using, this technology. And even there, you have reflections, of course. But when you get out into a harsh environment with many signals, so you have, interference, you have your own multipath interference, and as well as shadowing. Uh, there are many factors that are more dominant than the fidelity, if you will, of the circuits themselves.
Gotcha.
Yep, I
Heather,
think
anything
Plum
else?
says it best. Further proof, real life is messier than the specs.
That's right. Just because it's on paper doesn't mean it works in real life. I think we've times over our time together.
Oh, Daniel's putting some clarification if you guys can read that too. This question.
Um, Let me see. Let me go into the chat.
It's
To
based on
clarify the question, based on your automated diagram, that's the one with the little 16 QAM, it required 33% and 75% and 100% amplitude states, or minus 4.8 dB, minus 1.25 dB, and 0 dB changes. What is 1024 QAM? What percentages?
That's not actually what those percentages were. And in fact, I asked Erica, what is that? Those percentages look to be, they're actually just the increase in the number of bits. In other words, uh, that's purely a percentage of increase in number of bits, trying to indicate more information being sent. And of course, uh, each of those doubles in the factor of, when you go to 16 to 256, it's what, 4 times. And 256 to 1024 is 4 times the state's information. But no, that's just a simple
Well,
increase in bits, percentage of increase in bits.
let me share again really quick. I think maybe he was referring to this diagram right here. Can you see this?
no. Oh yeah, now we can.
Okay, and so with this, what we were talking about. You see where it says the amplitude 0.33, 0.33, then 0.75, then 1.0.
Oh,
You see that?
okay. Maybe I need to reread the question. Sorry.
Yeah. Okay. So it's like, okay, well then what's the amplitude when we're doing, 256 QAM or 64 QAM, what the amplitude will be?
Okay, well, there are a lot finer resolutions, and I don't have it off the top of my head, but if everything is just relative to one as the outer boundary, then you simply divide for 250, I guess 1024, you divide that by 32, right? There's 32 by 32 matrix for 1024, or 16 by 16 matrix for 256. So just divide that 1 by 16.
The point is, though, Don, is that it's not like it's stretching out further into space. We're cramming more, we're packing more into the same area. That's why
That's
it
right.
keeps
That's
getting
right.
smaller and smaller and smaller, right?
Yes. Mhm.
Yeah, I think that's the important piece to note. Okay, let me see if there's anything else. All right, good, good. Anything else in here? So with Wi-Fi 8, do we cross over to the fourth or fifth dimension? We may indeed. We're talking black hole stuff here, gravitational pull.
It
So
is an amazing capability. Where, it's not easy to think through what's happening on that carrier, that I can modulate it in two ways and they don't interfere with each other, and pull it back at the other end. There was a man, Charles Kahn, I think his name was, in 1960, wrote the first paper about this. And he is actually very much the father of GPS signaling, very well known scientist, engineer. So yes, it's something that's evolved during my lifetime, and is quite amazing.
awesome, awesome. Well, Don, thank you so much. I appreciate this. It's some people have an easier time, and other people have a harder time wrapping their head around these topics. To just, thankfully, there are really smart engineers and mathematicians out there who can do this stuff, because it allows us, like I said before, to go fast. So thank you
Right.
so much. I really appreciate it.
We've still got a couple more.
Go ahead.
I get to answer one. This is exciting. Will this video be available on the Seven Signal YouTube channel? The answer is yes. And you'll receive an email tomorrow morning with that link. But we've got a couple that just came in the Q&A panel. So first here, is there any other modulation techniques that you believe could be employed to break this 4K barrier, since it is becoming more and more complex to deal with the physics of RF and noise?
That's a big question.
Mhm.
I don't have a good answer for that. No. It's quite amazing, actually, how much the Wi-Fi standards groups have pushed the boundaries. As I said, 25 years ago, we didn't believe we could do anywhere near any of this stuff. And they, the standards get written before it's proven almost. I mean, it's proven in a lab somewhere, and then the standard gets written, and then it takes 2 generations of silicon to actually verify. The first generation, everyone rushes out the silicon, and it sort of works, but isn't impressive. And then when you go from N to, the next one, to AC to AX, and each generation improves the previous one, so then it works. But no, I don't. I don't know. I've retired twice, and I don't really know that I'm on the forefront of what's coming next.